Okay, so today we're going to talk about multi-electron atoms. Now, as you might guess, a multi-electron atom is an atom with more than a single electron. Up to this point, we've looked at hydrogenic atoms, which are atoms or ions with only a single electron moving about a positively charged nucleus. Now we're going to bump up our complexity to look at what happens when you have multiple electrons. Now, the first thing we have to think about is what do we have to keep track of in order to describe a multi-electron atom. So let's start with the simplest case, helium. Now, as we know, helium is a 1s2 electron configuration. You have two electrons moving independently about a positively charged nucleus of +2. So three things to keep track of: one electron, a second electron, and the nucleus. So here's how we can describe this. First, we have to think about the movement of the nucleus. Now, we can also think, because of the centrosymmetric potential, we can think of this as the movement of the atom as a whole, and we can use the Born-Oppenheimer approximation to separate the movements of the nucleus from the movement of the electron. So we'll set that aside for the time being. So if we're going to just set aside the nucleus, which is again the motion of the atom as a whole, let's focus on the electrons. So we have to think about what the motion of electron 1 is, what the motion of electron 2 is, and then think about what the attractive force between each electron and the nucleus are. So, as we know, because this is coulombic between the positively charged nucleus and the negatively charged electron, we're going to have two vectors, R1 and R2, which are going to be inversely proportional to the attractive potential energy. Now, the other thing we have to keep track of, because the electrons are both negatively charged, is the repulsion between the electrons. Now, this is going to be described by a vector between the two electrons, vector R12, shown here in purple. And this is what's going to give us some headache, because we can use the Born-Oppenheimer approximation to separate the electrons from the nucleus, but we really don't have a good way of keeping track of the repulsive interaction, because as we know, these are actually delocalized particles. Okay, so let's look at how we can modify our Hamiltonian to focus on the forces between each electron and the nucleus, and just set aside the repulsion for the time being. So again, we're going to use the Born-Oppenheimer approximation, so we only really have to worry about the motion of the electrons, and we'll just imagine this is that the nucleus is fixed in place. Again, not the worst idea, because the nucleus is far more massive than the electron, and again, that's really the motion of the atom as a whole. Okay, so first we're going to draw our electron Hamiltonian, which is h hat sub e. Now this is going to be used, we're going to use the same Hamiltonian that we use in the Schrodinger equation, except now we're going to have a term for each electron. So the first one is h bar squared over 2 times mass of the electron times the square of the del operator for electron 1, and then minus the coulombic attraction. So this is the standard kinetic and potential energy, and this is for electron 1. And then we have the exact same term for electron 2, except what's different here is that the del operator is for electron 2. It isn't shown in the equation, that's my typo. But you can see the two different variables are R1 and R2. So this Hamiltonian has taken into account the kinetic energy of each electron and the attractive potential energy between each electron and a nucleus. And this is also a manageable Hamiltonian. So here comes the hard part. Now we're going to add the repulsive term. Now if you'll notice, the attractive potentials are both negative, indicating that the potential energy decreases as they get closer, and the magnitude of the potential energy becomes greater as they become closer and closer. However, this repulsive part is positive, and as you can see, this is going to be inversely proportional to the separation between R1, the electron 1 and electron 2. And as you would imagine, this is very difficult to deal with. And this actually winds up being the death of the Hamiltonian, in that we have a doable part of the Hamiltonian, and then we have a part that we really don't have a good way of dealing with. So let's do what we do best. Let's ignore the difficult part and see how well does it work if we ignore this. So that's really the question. Is our Hamiltonian good enough if we ignore the repulsive potential, or is it still critical failure? Well, I think we already know the answer to this because we remember this from general chemistry, and that this is a good enough approximation that we can use with slight modifications. And this is known as the orbital approximation. So what we're going to do is we're going to describe each electron as being in an orbital, and that orbital is constructed from a hydrogenic atom. So if you imagine we have what orbitals we would have just for a single electron atom, we're going to use those to describe what each electron in a multi-electron atom is in. And then we're going to describe the total electronic configuration as a superposition of those atomic orbitals. Now the key is, if this is sufficient, meaning that the descriptions, the geometry of the atoms, the spectroscopy are good enough, then this is good enough. However, if this doesn't work, then that would mean that we'd have to really look carefully at how we can best refine this. So again, this is a superposition of orbits that we get from hydrogenic atoms. Okay, so if we're going to look at our electronic Hamiltonian, we should look at how we can construct this. And again, we're going to stick with helium just because it's the most convenient, nice two-electron atom. So our Hamiltonian for the electronic part is going to be a combination of the Hamiltonian for electron 1 and plus the Hamiltonian for electron 2. And then in general, for any multi-electron atom or ion, we could just reflect as the total electronic Hamiltonian is simply the sum of all the Hamiltonians for each of the electrons. Okay, so with the Hamiltonian taken care of, we should look at what happens to our wave function. So we're going to use the fancy psi for the time being because we're going to have this for multiple electrons. So our Schrödinger equation becomes the sum of each of the individual electron Hamiltonians operating on the atomic wave function, and this is going to be equal to the sum of the energy of each of the electrons times the wave function that they started out with, as shown here with the energies in red. So you can see that we get the exact same thing as we would get for looking at one electron, where we have the Hamiltonian operating on the electron wave function, giving us the energy of the electron times its wave function, as we do for an individual case, and all we're simply doing is summing these together. So this is the heart of the orbital approximation, is that we can treat each electron as if it was in an orbital, again described by this hydrogenic atom. So here we have an energy because of energy associated for each orbital, and this holds true because of the Pauli exclusion principle, where we know that each electron has its own set of quantum numbers, and each orbital is going to have two paired electrons, and of course the pairs refer to the spins. Okay, so with that taken care of, now we should turn our attention Okay, so we're still sticking with helium as the two-electron case, and we know that our wave function is going to be a linear combination or a superposition of all the possible states. And again, we just have the two electrons here, electron 1 in state A and electron 2 in position or state B. So our wave function is going to be wave function for electron 1 in position A or orbital A times the wave function for electron 2 in orbital B, either plus or minus the wave function where the electrons are switched, electron 1 in orbital B and electron 2 in orbital A. Alright, so because we know each electron will have its own set of quantum numbers, again back to the Pauli exclusion principle, we know that we can uniquely describe the energy of each of the electrons. Alright. Just give me a minute while I let my slow writing catch up to my fast voice. All right, so what we want to do now, we want to, not to fall back in Gen Chem, but remember general chemistry is describing what's actually observed, and quantum mechanics doesn't do that, and it's not working very well. So again, we're looking for confirmation that the orbital approximation is a good approximation. So we're going to look at periodic trends within using the orbital approximation, and again, this is going to be a gauge of its effectiveness. So if you recall, penetration and shielding, if you remember that when you're doing electron filling and you're calculating effective nuclear potentials, all those fun things in general chemistry, here we go again. So what this boils down to is that closed shells, meaning completely filled orbitals, which especially with the principal quantum number. So when n is equal to 1, that would be 1s2. When n is equal to 2, that would be 2s2 plus 2p6. The closed shells shield the outer electrons from the nuclear charge. So what we wind up doing is having a reduction in the nuclear potential, which is Z effective, shown here in purple. And that's going to be equal to the total nuclear charge minus the number of electrons, or the negative charge, in these closed orbitals. So next, we'll look at some of the radial wave functions and see how shielding works.